Hello, my name is Tiago, and in this video I'm going to talk about the phase lead controller applied in a single phase grid connected inverter. This phase lead controller is more used in DC-DC converters, but I can show you here that we can use also in a single phase inverter. This phase lead controller is also known as integral single lead controller, second order integral lead controller, and type 2 controller. So you may find these names in few books which deals with the same phase lead controller. In this video I'd like to show you the power structures that I'm going to simulate, the controller itself. I'm going to run a simulation here in LTspice, and of course the controller will be analog. It means that we are running this simulation in a continuous time domain, and I'm also will talk a little bit about the script to design this controller and give some considerations in the frequency response of this controller. Let's get started with the block diagram here, the power structure. So this is what I will simulate later. I will just simulate a single phase inverter which is made by a H-bridge converter. The output filter is just an inductor with its copper resistance, and also I have here the grid with a short inductance. And the variables that I'm measuring to run this controller are the output current as well as the grid voltage. After measuring these two currents, this variable go here to the lead compensator plus PWM, and then later I will apply this to the transistors to run the structure. If I move here to the controller, this is the analog phase lead controller. This controller features the ability to have a pole at the origin and also a zero pole pair in frequencies located depending on the design specifications. If you take a look at this controller, I mean that the input is the error, so I just compute the error, which is the difference between the reference and the output current that I'm controlling, and the output signal is just the controlled signal. There is a notification here that the error must be multiplied by -1 because this operation amplifier is working as an inverter, so this will invert the signal, and as a result I need to compute the error by computing the difference between the output current minus the reference current. So this phase lead controller will be designed after computing the values of these components. Since I have a script, a procedures to compute these components, I can consider that the controller is designed. And of course, to compute these parameters, there are some specifications, some criteria that I'll show you in a moment. If I go here to the script, I have here a script to compute those coefficients, but before describing this script, and of course this is not the intention of this video to describe line by line how I designed the phase lead controller for single phase converter, I'd like more to emphasize here on the frequency response of such a controller. Let's run this script and plots a few board diagrams. Just a moment. If we start with the frequency response of the controller, which is this one, we can see here that the controller itself adds -90° into the system, but this is the feature that this controller holds, which is a phase lead at such a frequencies that we can define later. But the intention is to show you this board diagram is to show this kind of behavior that makes the phase to go up here related to the steady state phase that we have here in this controller. If you take a look at the magnitude of this frequency response for this controller, we see here a kind of a decaying line, which is good because this will make the error to go to zero in steady state. This is the frequency response of the controller. Let's take a look how to design this controller, and then I will show you different board diagrams for other parts of the system. So let's take a look here in the script, and again my intention here is not to describe line by line how I designed this phase lead controller, but the idea of this video is just to give you an overview and show how this controller behaves, and also test it with disturbances and other things in simulation. But To design this controller, you just can't follow a single procedure. You can find also the procedure very well detailed in one of my papers that I published. So, but the script here just starts with the system parameters, and the point that I'd like to highlight is that this controller, the procedure to design this controller starts with defining two parameters, which are the desired cutoff frequency. So I'm defining here a cutoff frequency for this controller, and also I'm defining a phase margin in which I want this controller apply to the system. These two parameters are quite important because the cutoff frequency will tell us about the bandwidth of the controller, so we can define how far, how long is the bandwidth of this controller. In this case, I'm defining here 10 times lower than the switching frequency, which is also a recommendation from the control theory to have a good behavior of the controller. Just defining our cutoff frequency as at least 10 times lower than the switching frequency. And the phase margin I'm defining here as 60 degrees, which is also a recommendation from the control theory that any phase margin between 30 and 90 would present a good response in our controller system. So, but defining these two variables, we can take can take a look later if the controller is actually applying these two recommendations. But after defining these two parameters, we are going to design the controller. Just take note that my cutoff frequency here will be 4 kilohertz because my switching frequency is 40, and my phase margin will be 60. Memorize these values because very soon I will check if my controller is properly designed by checking if the system presents these two variables. So after following here a script to design the controller, I can simply run here this script and check the both diagrams. It takes some time. But if you take a look here at the both diagrams that I'm plotting in this script, let's start here with the first, which is this is the frequency response of the system without the controller. We can see here that this is flat at low frequencies, meaning that the error will not be completely zero in steady state. We also have here a shape for the phase. Again, this is the frequency response that I previously described. This will be the result of my system in open loop, but considering the controller, we can see here at low frequencies that we have such a decay, which means that the error will be zero, and we can see here the phase lead that the controller is applying to the system. This last board diagram here shows the closed loop frequency response, which is good because my cutoff frequency, as I said, is 4 kilohertz, and I can check here that in 4 kilohertz I have the bandwidth of my controller, which means that the controller is presenting 0 dB as gain, which is 1, and we have 0 phase for all up to 4 kilohertz. This is good because my bandwidth has such a large value. Any frequency that I'm applying to the reference will follow the output controller volt current will follow the reference without considerable error. And this is the closed loop control system frequency response. I can check here if the phase margin is actually what I defined, which is, I can see that for this system, this one, the phase margin is 60 degrees, which is good. And also I can check if the cutoff frequency that the system is presenting due to the inclusion of my controller is actually 4 kilohertz. Let's take a look. If you take a look at this variable here, which is the cutoff frequency of the system, if I divided this by 2pi, because the frequency is in rad per second, let's check the frequency in hertz. Let's see, which is actually 4 kilohertz. So this means that my controller is properly designed because I started with the assumptions that I want a cutoff frequency of 4 kilohertz and a phase margin of 60, and after compute all the coefficients I can see here in the bold diagrams as well as this in this large final command here margin that my phase margin and cutoff frequency are as expected. I can check here also what were the controller parameters R1, R2, C1 and C2, because later in my simulation I will apply these values in this controller. Moving to the simulation, allow me to explain how I implement everything here on LTspice software. I'm here with H-bridge converter with MOSFET. These MOSFETs I just randomly selected here on the libraries of LTspice. I was concerned only on picking a MOSFET which has a VDC voltage higher than the voltage that I'm using in the DC link. By the way, I'm using 225 volts in the DC link and my grid is 127 volts RMS with 60 Hz. So the peak of this voltage in the grid is 180. This is a common value here in Brazil. In the output filter of my converter, I have an inductor, and I have here the representation of the copper resistance of this inductor. For measurements, I have two variables being measured. One is the output current of the inverter, and another one is the grid voltage. This grid voltage is necessary first to make a PLL in the future, and also to act as a feed forward in the control strategies as I will describe in a moment. Coming back here to the output current, I'm using a shunt resistor to measure the output current. I designed this controller to have 20 amps as output, 20 amps peak as output current. So after passing these 20 amps through this resistor, which is 1 milliohms, I have this value 0.02. As my intention was to design the controller in a per unit frame, I need to multiply this by 50, which is equal to 1, resulting that my controller is actually working in a per unit system. When I apply a reference equals to 1, this will result in an output current with amplitude equals to 20. Here on the voltage sensor, I'm using 1 over 180, which is this value, and also this will account as a per unit control strategy. Going back here to the PWM, this is the PWM. I have here the carrier, which is a triangular waveform. As I'm using a per unit system, my carrier is vary from -1 to 1. And I have here the comparator signal, which is the output control signal of the controller plus the grid voltage scaled by the sensor gain, which act as a feed forward action. I have here the comparator and some compensations. Here's the inverter part just to produce the positive and negative pulses for the H-bridge converter. If you go back here to the inverter, you can check where these signals are applied. The positive pulses and also the negative pulses are appropriately applied to the MOSFETs. So my triangular is from -1 to 1. My frequency is 40 kilohertz, so I had here the period for this switching frequency. And talking about the controller, I just put here the variables that I computed in that script. After computing all the coefficients of this controller, I have just typed it here. I'm using here the operational amplifier as the controller. This is supplied by +15 and -15. So as I'm using per unit, this will be restricted to -1 to 1. Of course, this is not so good because I could use a triangular carrier vary from -15 to +15 in order to have a better resolution of the controller. I will use the full range of the operation amplifier. This is not my case. I usually prefer, when employing analog controller, keeping from -1 to 1. I'll show you later that this signal is within such a value. The controller is not saturated. For the reference, I'm using just a sinusoidal waveform, but I wrote here that this must come from a PLL because of course here in simulation my 0 degree here is synchronized with this 0, which is not typed here, but both sinusoidal waveforms are synchronized because of course this is a simulation. In real applications, we need to make this sinusoidal waveform to be synchronized with this, of course through a PLL. As this is not the intention of this video, I will keep this sinusoidal reference just as a sinusoidal source. Let me see if there is something else, otherwise we are going to simulate and check the results of these controllers. Before running the simulation, I'd like to say that there are several ways to test your controller. Of course, the first option to test your controller is to verify if your controller is running with the parameters that you initially defined in the design procedure. In my case, is an output current with 20 amps as peaks. Let's simulate this and check if the output current is actually that one. By measuring here the output current, I can see that the output current is a sinusoidal waveform with amplitude equals to 20. So my controller, I can conclude initially that my controller is properly designed. But instead of measuring the output current, I will erase this. I will include here the output signal of the sensor, which is a sinusoidal waveform representing the output current but vary from 0, -1 to 1, and I can check together with the reference to see if they are coincident. If I apply a zoom anywhere, I can see that my output current is following the reference as expected. So this is the first test to verify if the controller is good. Another test that I'd like to apply when I design controller is to change the reference from 20 amps to 10 for 100% to half percent. Let's see. So I will include here a voltage which will be a step. If I define this voltage as a step, vary from 1 for instance to in 30 milliseconds, see 1. If I change this to 0.5 to 0.5, this will be a step down, varying the reference from 20 amps to 10 amps. This is a test that is good to apply because the controller is usually designed by an equilibrium point, but we're going to see that this linear controller is also good to work in a different operational point without modifying the parameters of the controller. This is the step. Let's define here a variable like step, which is just our step. This I will change to sinusoidal, and I will include here a behavioral voltage to multiply these two new voltages, and this will be my new reference. Let's define here the reference, put in the ground. So what I have just done here is apply the reference step in which will vary in 30 milliseconds from 1 to half, which means from 20 amps to 10 amps. Let me define this voltage, which means voltage of step multiplied by voltage of sinusoidal source. Let's see what will be the result. My current is initially vary from -1 to 1, which means -20 to 20. In 30 milliseconds the step will happen. We can see here how the controller behaves in the system. It seems that the controller is working good, even for the reference from 20 to 10. This is good, this is enough. But this also shows us that the controller is properly designed. I can apply a zoom here just to check how is the output current following the reference, which is good. This is the first step I'd like to test. I can also try, for instance, vary from 0 to 1, which means the initialization process of the converter, or a standby mode. So you are in a standby mode with output current equals to 0, and suddenly we have the nominal current at the output terminal of the converter. This is also a good test to apply to check if the controller is able to operate under a 0 reference. This is the result. The result is quite oscillatory, and if you want to change this, because you may consider this transitory behavior quite severe, you can apply, instead of this step, you can apply a ramp, which will gradually enhance the amplitude of the reference signal. Again, instead of applying the full nominal current, we can apply a ramp, which will gradually increase the amplitude of the reference, and this transitory behavior, of course, will disappear. Let's return here to from 1 to 0.5, and let's emulate again just to check if everything is okay. And then I will include here a disturbance in the DC voltage. I will include here a voltage in series of our DC link, and this will be sinusoidal with amplitude equal to 18 volts, which means 10% of the grid voltage, and the frequency the double of the grid, which means an oscillatory mimicking a rectifier, for instance. Let's stop. Okay, this is still good. Let's simulate again with the inclusion of this disturbance in the DC link. So even in the presence of the disturbance, I can see here that my output current is following the reference in a satisfactory way. Applying zoom, we can see that this is good. Let's wait for the transistor, which is also good. This controller, so I can conclude that this controller is good to reject the disturbances found in the DC link of our system. This is enough. Okay, I can include more things here. For instance, let's include an impedance in the grid. So I can just move this source a little bit to here, include an inductance. Let's put here, for instance, 600 microamps. Simulate again. Okay, remember that remember that I have the disturbance in the DC link. Now I have the inductance in the grid, and also I have the step in the reference. Everything is good to check if the controller is properly designed. So far we see that this controller is quite good. The bandwidth of this controller is 4 kilohertz, as I said. So you can see here actually this controller is good. Just checking this voltage, you see that this voltage is oscillating. Another thing that I'd like to test in this controller, if you go back here to the frequency response in a closed loop situation, we see that the frequency cutoff frequency is 4 kilohertz. This means that the controller will be able to operate with any frequencies between 0 and 4 kilohertz with steady state error equals to 0 or approximately to 0. What I'm going to do now is to return the reference, return the reference to a sinusoidal, but instead of, let's change this to reference again, but instead of just having a sinusoidal waveform, I will have harmonics being injected into the grid. Intentionally, of course, because my reference now has this reference, which will be 0.2 in 300 Hz, 50 harmonics. So my reference now has harmonics, just to show that this controller, due to its large bandwidth, is able to inject current with harmonic content, and this is still making the output current following the reference as expected in a good way. So we can see here. Due to the large bandwidth, let's include one more. For instance, this is quite common, the 7 harmonic. Let's copy this here. If I change this frequency to 420, it could be this amplitude just to show. Let's simulate again. We can see that the controller is still making the output current follow the reference, even in the presence of this high harmonic content. As a conclusion, we can see that this controller is quite good to reject disturbances, to work under grid impedance. Of course, there are a lot of improvements that we can do here. For instance, modifying a little bit the controller to have passivity feature and external stability and other stuffs. But as a first moment, I can conclude that this controller is quite good. It can work as an active power injection, but it also can work as active filter, because just having one controller with a large bandwidth we can see that this controller can inject harmonics without modifying the controller. Just a final test. If I come here and erase this, since my controller is under per unit system, everything is under per unit, my triangular is from -1 to 1. I can check here the control just to see if it is within -1 to 1. Also this one, let's see, everything is between -1 to 1. It means that the controller is not being saturated. And if I take a look at the triangular waveform, it is actually also between -1 and 1, which is good, which is as expected. So everything is within the range of -1 to 1. Going back here to the simulation, let me see if I have final remarks of this system. As I was saying, my controller is under per unit, everything is from -1 to 1. My operational amplifier is from 15 to -15, but again, this is not a problem. I'm not using the full range of the operational amplifier. This has some drawbacks, but you can use, for instance, a triangular waveform vary from -15 to +15, but you need to consider it in the controller design, as I included here, carrier amplitude. But of course, in real applications, in hardware applications in which you are going to employ analog controllers, you want to use the full range of the operational amplifier, as well as this will be also generated by operational amplifiers, so it's more appropriate to use -15 to +15. The intention of this video is just to show this controller for those who are not familiar with this controller, and also to show its frequency response and its behavior under several disturbances and reference changes in this situation. Well, so concluding, the controller actually works good in a grid connected inverter using MOSFET switching at 440 kHz. I hope you enjoyed this video. Thank you very much for watching.